following the trend of my last videos on, revisiting algorithms that I have already visited in the past, I wanted to take a look at, I wanted to revisit the quantum Fourier transform as well, the QFT, which is, now that I think a bit about it, wait a second, that's just so nuts with the animation. It's pretty nice though, but I'll just stop that. So now that I think about it, I think this should be fairly straightforward. I think I didn't get it really wrong. Let me take a look. What do I have if I go to YouTube? And I go to my channel, your channel. So, and I should probably, I don't know, if take a look at lists, the playlists. Oh, here you've got like, okay, so 7 videos on the QFT. That's a lot already. So quantum Fourier transform, how to encode a QFT, almost got it. QFT, does this make sense? Now, I have to admit I'm still confused with one thing, which is, it seems like, and I'll probably tweet that, but it seems like Craig and some people call the QFT, the quantum Fourier transform, the algorithm that takes you from like a frequency space. So the input here is like, what's the frequency, right? It's like 1, or like it's like 2, right? And then you run through the algorithm, and then you basically, if you consider that your sample, like each of the possible states, your sample, starting from this one and ending with this one. So you wanna, in this case, encode a sort of a wave in your phase, in your relative phase, in such a way that it corresponds to that frequency. So if I'm putting number 2, I want the relative phases to cycle 2 times between this, the 0, 0, 0, 0, 0, 0, and all 1 state. So, and it's kind of, I think it's what it does, right? Because it starts like that, and then it starts, it does all these, and then this is roughly the half, and it's exactly where the number 1 is at its highest value, right? The number, and it's everything else 0. So you can see this in this hover information, and then you go, and then it does the same thing here all over again until you end up here again. So, if I would just basically put a 1 over here, literally, what does it? How many times? That's a lot of times. Yeah, it's kind of, it's almost doing a full circle every time, like a full cycle, I think, right? I mean, the most would be like if you do like these, right? It's all ones. Oh, I had that one on still, so that was kind of wrong. But then, wait a second, there's something off, because that is like, that is not what I expected. Seems like it does 2 rounds. Okay, that's weird. So you see, I mean, but anyway, so my point is, some people seem to call these like, that's a QFT, right? So give us, or give the algorithm a frequency, encode it in this register, and then you basically get a wave that, the corresponding wave on your phase, relative phases. In theory, if I remember well, you can as well input like more than 1. Why can't I go back? I know there's a, because I'm using touchpad, and I know there's, in theory, if you, so this should work this way, that if you basically manage to encode like two numbers in here, like with high probability, like 1 and 2, for example, then you should actually get a wave that's composed of those frequencies. And that's kind of the same. But what's confusing to me is that if you take a look at, you know, um, channels that explain what the Fourier transform is, like Fourier transform. So you've got like where you've got like 3 blue, 1 brown, obviously, which is a really nice visualization. But here it's like they talk about the Fourier transform as like you're going from the actual wave to the frequency space. So that's what's confusing me, because different people talk about this in different ways, right? So Craig seems to be the one that says, that's QFT, and then or at least he calls that QFT, right? So if I refresh quantum Fourier transform, and that's what it takes you to, right? So the animation is here just for displaying purposes. But and then if you go to, so then correspondingly, if you take a look at Shor's period finding, he's using the inverse of the QFT, because that's what you want to do in Shor's algorithm. Is like this gives you basically a wave-like thing, like a wave, like a pattern in the phase that you want to decode in terms of what's the frequency. So you apply the inverse of the QFT as defined by Craig. So, but I don't know what's the standard, because then if I go and take a look at if I don't know, I can find this, but in the book, in the O'Reilly book, can I just go to my Kindle Cloud Reader? Am I still gonna have? Because I don't know if I have the actual thing paused, or but is it going to allow me to access the books? Yeah, it seems like. So this is basically the O'Reilly book, and then if I take a look at QFT, right? Quantum Fourier transform. So the way they present it is like you have the stuff encoded in your phase, and then you're actually getting the frequencies. So it's the opposite of what Craig does. And but I think the book still has a mistake, because when they talk about, and that's QFT, so you would assume the inverse is from frequency space to the wave. And then if you take a look at Shor's algorithm, I think there's still an inconsistency. Shor's factoring algorithm, I think there's still an inconsistency here, because according to their own definition, Shor's should use the QFT, not the inverse, right? But then Shor, when they do this, they say factoring number 15. So there's an example of factoring number 15, and then did they fix it? Where was that? Superposition condition multiplied by 2. No. They use QFT. Okay, so seems like they fixed it. So in this case, blah blah blah, experiment with different since the spikes are evenly spaced, we know the size of our register, we can estimate how many spikes there were in the QFT, even though we can't hope to observe more than one of them. This is more indirect. From our estimate, we know that this number of peaks is the same as pure P if I precisely what we're after. It's a more indirect use of the QFT than we covered in Chapter 7, but it demonstrates a crucial point. We shouldn't be afraid to use all the tools at our disposal to experiment with what's in our QP registers. Okay, so it seems like they fixed it because I think this was wrong. So cool, that's nice. Um, yeah, but still, but still, I don't know what's the best thing to do. Whether I shouldn't just do it on a pull request, or maybe I'll just ask him. Um, worth a pull request, but isn't the QFT linked and quirk actually the inverse QFT? Seems like the input is the frequency. Or am I missing something? I mean, at least in the classical the classical Fourier transform is seems like it's from wave so from to amplitude to frequency kind of thing. Why? Of course, I'm not gonna be able to paste that. Cool. Let's see what he says. Good. Having said that, let's get to basically breaking down the whole thing first in this video. See how far we can get, and I might do a second one on this probably, because I really want to get a bit. Oh, what else had I done here? So I touched almost got it here. Okay, the nomads, then a bit cringy, but okay, so the inverse QFT, Fourier transform is native to quantum computers, for instance, native to quantum computers. Why is it linked twice? I think I should get rid of one. Okay, yeah. So I really haven't done much more than that. So it's just 6 videos. I mean, this one was actually more linked to Grover's algorithm than to this, but I'll keep it there because it kind of makes sense. So let's break this apart. First things first. So of course, obviously, I'm gonna try to reduce dimensionality first because it's gonna make it easier to operate with 3 qubits than with like, what is that? 3, 6, 7, 8 qubits. It's a lot. I mean, I get that you probably get a lot of like you can appreciate the gradient or you can appreciate the rotation better when you have so many different relative phases to take a look at, but it's just gonna make it difficult for me. But so what do I see here? So basically you've got the initial state, right? Here. This is just separators. So the first thing that is catching my attention is this. My initial guess would be this is because of the way this is being represented in terms of. So this is whatever it's called, big endian, little endian. I don't know which one is what, but I mean here, like if I flip that, it's gonna be a 1. So this is the lowest bit in a bit string, right? The lowest value, like the units, right? And so and then that would be like 1. That would be like 3 in this case, right? That would be like 7. So, and I'm guessing the swaps are there because what you probably high level want to do with the QFT is you want to kind of rotate the phases of each of your qubits based on how much weight they have in the overall number. Like obviously this qubit has less impact, or should have less impact on the overall rotation or something like that, I think. Whereas if you've got a 1 here, that's kind of telling you, well, if all you have is 3 registers and you have a 1 here, you should at least be halfway, or you should, how to put it, halfway. uh, the other way around. uh, Okay, so if you consider that this is supposed to be the frequency, right? If you've got a 1 in here, that's why it's okay. That's why. So the one that usually has the qubit that usually would have for your representation the lowest influence in the number. So 1 is sort of the lowest, is the unit, as I said, like the last bit in your bit string. This is actually going to have the biggest impact on the whole rotation scheme, because this really looks like a rotation scheme, like, or rotating architecture, however you want to call it. And so this is going to have the biggest impact, because if you've just got a 1, let's assume you just got a 1, this means you want to do a full rotation, given, like, if you've got here like 8 qubits, right? You've got like all these many states, and so you wanna basically do a really granular rotation, because you just want to do one full cycle, right? One full cycle. So that's like really little steps in each other times. So that's why this one here, let me change the color, pink. So this one here kind of travels and goes down here, and then all the way, and then it's used as a control for like a bunch of rotations. um, because what you basically want to do is you want to rotate across all the different uh, possible states, right? Because a rotation, we'll get into rotations now, but like a rotation here basically means that um, all the different possible states that have a 1 here, so that would be you know that would be a thing, right? This entire row, this entire row, this entire row, this entire row, right? So these 4 rows here, they all need, like, so they're all gonna rotate, but then okay, so you're applying already like an S, which is basically like a halfway, it's like a quarter rotation. And then, but then you're gonna subsequently, for all the other qubits below that, right? Um, so there, where you've got like a 1 in the third place, so that's like this here, this here. So I should change color to yellow. So that's like this one here, this one here, this one here, this one here. This one here, this one here. So all those, they also get a rotation. So the idea is um, that by piling up those rotations, you're getting the effect you kind of see here in your 1.5. That intuitively, that's what's happening. So you've got all those rotations, right? Like, and they are all controlled. That is technically part of that as well, I guess, but that's kind of your rotation scheme. And then each of those columns is controlled by the weight of a particular qubit here being turned on, like as a 1, because that means that if it's a 1, it has to be correspondingly rotated. So if you've got like um, if you've got like 1 1 1, you're also you're each of those qubits being turned on means that you need to activate like the rotations for this column here, for this column here, and that is Hadamard in and of itself a rotation in the sense that if you got a 1, it's going to take you to the minus state, which is it's the same as doing like a 180 degrees phase, right? On a qubit that's 0, and then you basically go to a superposition and then do a Z gate. So and I think those are the pieces. So basically basically this is how I would break it down. I'm gonna try to reduce dimensionality now, but this is, I think, it. Here the Hadamard gates, right? So that's another component. This, you've got these Hadamard gates in here. What are they useful for? So basically, I think that it's two things. You need them because without them, you're not gonna get into a superposition for that for that particular each qubit, and so the rotations that you want to apply won't make any effect. I think that's one obvious reason for this Hadamard gates being there. Second is that they are they behave in the edge cases of the lowest, like the upper here qubit and the one at the bottom, they actually behave like a rotation. So literally, if you've got that qubit in the one state, that Hadamard gate is going to take you to the minus. So it's going to take you, you know, if you that's your block sphere. Oh, that's bad. It's going to take you to the minus state here. So you're effectively have a 180 degrees phase already out of the box just by having that Hadamard gate. Um, yeah. So I think that's how I would basically break it down. Um, Now I want to play with it a little bit, trying to understand how the rotations are laid out and if my understanding here is correct. So for these, I'll reduce dimensionality, play with some of the values. Um, but I think it's fairly easy. At the intuition level, it's fairly intuitive. But it's another example of those things where, I mean, really each and every time when you're facing a quantum circuit, you cannot, like, there's no one out of the box way you can take a look at those operations. I mean, Hadamard gates here have, you know, they serve a specific purpose. Um, but you could take a look at them from a different perspective and you might, you know, kind of be confused. But it's interesting. If I go back to my if I go back to basically what was that, the Kindle Cloud Reader, cancel, no, search QFT techniques, how does here look like? Because here's it's slightly different, as in so here basically you've got okay, so interesting. Here you've got a preparation, which I don't know what it does. Okay, nothing. That's if we just focus on the QFT. What they do is they wait a second, but that's still okay. So I should look at the inverse actually. So I should look at it from that perspective, almost kind of. But weren't they talking like about the inverse as well at some point? I thought they were talking about the inverse QFT, the DFT. QFT is fast. The inverse. Oh, here you go. So okay, so you've got that concept of preparing your frequency, and then okay, and then you know you see the same pattern. So there's like a bunch of swap gates, and then okay, the only thing they do is they have the Hadamard gate patterns as well, and then they actually have control Zs that basically create basically packs them into like a, like a control with multiple targets, which is a more compact way of writing that. So this will be, because here's like, okay, 90 degrees, so this will do 90 degrees, this will do 45 degrees, this will do 22 and a half degrees, etc. um, and then those rotations here, they're just packed into one column, like they're compressed in each of those columns, right? So they are all huge control Z's with multiple targets. And you've got, so it's the same, okay, so it's kind of the same. It's just, again, calling it inverse QFT or not. Okay, cool. So that makes my life easy, because I don't have to think about it a lot in terms of what's wrong, whether there's something wrong or not. So how would we reduce dimensionality here? First of all, if we're just doing 3 qubits, right, I just need to get rid of a lot of things in here. So basically everything that is, let's do 4 qubits, because at least I'm gonna have that step in here, and then I can get kind of rid of all this stuff, right? So I get rid of all this, get rid of all the swaps in here. I'm gonna need basically just, just 2 swaps. So where's the swap in here? Can I just, yeah. So I'm gonna swap like that. I'm gonna get rid of these separators. I'm gonna get all these guys back to 0. Yeah, that's much better. That's much more visible. So let me bookmark that. Call it QFT 4. Cool. It's gonna be easier to see stuff in here. Perfect. Where was I? Sorry, I stopped. I paused the video because I had to take care of something. But so, and by the way, this is the inverse quantum Fourier transform. So it's the easy one, I think. At least that's how they put it in the book, and it is easy conceptually, really. I mean, but let's try to break it down. I mean, let's try to understand what's happening in between each of these steps. Yeah, let's see that. So we've got obviously 4 qubits, right? So yeah, so basically 16 possibilities. And let's see what happens. I mean, when 0, obviously, there's no real wave or anything here encoded. And when I say wave, like what I mean, if you say 1, for example, right? So you can see that each of the, like in each of the different possible values, the phase is rotating. So this is, here's 0 degrees, here's 22 and a half, and that's the 22 and a half that you can see in here, right, as well. So here's like 45 degrees, here's 65.50, here's 90 degrees, so, and it goes. Here's, it's done half rotation, because remember that 1 means that we want to do a full cycle given the amount of states that we have available, that corresponds to the number of qubits that we have, of course. It's like the power of 2, so it's like the power, obviously. So what this would translate is, this is a way you encode a function that if this is your one axis and this is the other axis, you can imagine, like, if we consider that to be like the full cycle. So what you want to do is sort of, I don't know if I'm gonna say something stupid right now, but you want to do something like, that's like full cycle, right? Because then it repeats. So this is the part you're encoding here, by basically rotating, right, and saying this is 0 degrees, and once we give a full cycle, we want to be at 0 degrees again, or kind of almost, right? Because that's not exactly that. So it's one step before that, and halfway we want to be here, right? So we want to basically be half done, like a half rotation. So um, and so this you know, if we were to discretize that, and you know, it's not a continuous function, but it's basically different steps. Like each of them would kind of belong to, you know, we kind of encode each, like one of these ones here. So that's what we're encoding in here. Um, and yeah, so basically that's it. So if we are gonna go all the way crazy and do this, right, it basically, so what does this mean? So this is basically telling you that you want, telling us that we want 15 rotations, right? 15 rotations within that. And that, by the way, really is kind of, you know, you should think of this as it's your degree of sort of accuracy, right? So if you want to be able to represent really fine-grained, like for example, so 15 rotations in when you've got 16 possible states, that's just stupid, right? In the sense, stupid. Sorry, it's not stupid, but it seems to me to be a bit um, useless, because you're like between here and here, you've done almost an entire cycle, and that's kind of like you don't get the, you don't, it's really discrete, you don't get the granularity in between those two rotations, right? So really what's going on here is that in between these and these, there's been like a you know, like a almost full rotation, um, right? That's why, so it's pretty funny, because you would think that this is rotating counterclockwise, because you're saying, oh, first is this, then is this, then is this, then is this. That's counterclockwise, but it's not. It's actually, sorry, clockwise. Oh, it's rotating counterclockwise, right? Remember, this is 0 degrees, and it's rotating this way. And so the step in here is that you've almost got a full cycle, because you've got 16 possible. So we've got a sort of 16 um, different boxes, right? But we're saying we want 15 rotations within that space. So it literally means that between one box and the other, you almost have to rotate fully, and that's what you get. So don't let, it's easy to get fooled by this, but that's what's happening here. Good. Um, so let's take a look at the effect that each of those things, I'm gonna, each of those steps is kind of doing by just placing measurements in between, and I think that should be enough for the video, for the inverse, because it's fairly straightforward. What's not that easy to understand is the 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 actual quantifier transform. Intuitively, you can think of these, or the way I think about this is, you're kind of unfolding, like, so this is, for me, it's more like you're unfolding, right? So you have these here, and you're unfolding it into all these different rotated phases. So the quantum Fourier transform, which is the inverse of the inverse quantum Fourier transform, for me it's more like you are intuitively, I think about it as I am folding my function in a way that I will end up with the actual frequencies it's made of, sort of. That's intuitively, but that's, I think, what I basically ended up with in the last videos about the QFT. So, but let's see. We'll just first focus on the inverse, which is the easy one, and I'll make another video for the QFT. So if I put amplitudes in here, so, and that's why I say unfolding, right? Because pay attention that this is what the Hadamards do as well. They don't only serve as a rotation, they also serve to create the actual full superposition, because you're, at the end of the day, you're doing a Hadamard per each qubit, right? So you're getting an actual superposition. So the when we when we're at that step, right? We apply a Hadamard in here. So what's being executed right now here? So this Hadamard happens. That's what you have in here, and the Hadamard puts already your the last box is already rotated halfway, and this is not rotated at all. Okay. So give me a second. I won't do it this way because this is too messy. Because this is too harsh. So I'll do this with like A2, which means we want to give 2 full circles here. So you're doing like that, and basically here you're in the middle of it, and then you end up right before, like, the next step. The next box would be, you know, closing the actual cycle. So I see this way. I can see better. See better what's going on. It's pretty interesting. So now it's basically unfolding, but from here. So it's unfolding the starting, of course, because you've got 0, 0, 0, 1. Sort of. I don't think it's relevant where this really starts, but the fact that you've got a Hadamard gate, but because this is 0, there's no phase shift anywhere here yet. So as of yet, it just, you know, it just unfolds a little bit. So this means you start to create the superposition. Interesting. But remember, because of the swapping that's needed for the right controls to be activated, this one really goes down this path. So it's going to activate only these, and nothing else is going to be activated for that particular input. So I'm just going to move it because, or maybe I'm going to create another one. So here, if I mean, essentially, if I move it here, nothing has happened really. Now the Hadamard will actually make a change. So now we have another Hadamard in here that basically unfolds that even more. Now is where it's getting interesting. So how can I? Because if I do this, we're gonna miss. So now we've already basically rotated everything we. Let me do this step by step. So what if I basically clean that thing and separate that into two different so I can see what's the effect. So I'm gonna put the amplitudes in here, and we can see the first rotation, which is the one that basically affects that qubit. Which is basically the qubit where, so why are we rotating these two here? 0, 1. If we swap these ones, so you're rotating these by 90 degrees. The swaps are confusing me. When and a t is like a half of a quarter, so it's like an 8. And so you're doing it for uh, sorry, it's just confusing me because of the swaps, but I mean those things are just affecting the two particular wires. So this one and this one, the two lower ones. So this is affecting the one. This is affecting. Oh my god. This is affecting the two lower. Yeah. The one. So the one. 0, 0, 1. Trying to think. 0, 1, 0, 1. Yeah, yeah, yeah. Okay, so this is affecting the one because this is so confusing. Um, so this is I cannot. This is affecting the second qubit. This is rotation is affecting the second qubit starting from the right. Um, that's why it affects those two boxes. And the contribution. Pay attention. Is always the same pattern. So the contributions are the contribution of these is um, the contribution of uh, the contribution of the first qubit after the control is always an S and then a T. Is ST, and then you start with a Z with like an eighth turn. And so what's T then? Whatever. So you are then increasing the power of 2 because that's this is in base 2, right? There's a binary. It's like 0, 0, 1, 0. So that's how you represent the influence of each of those wires. And so this T basically rotates the lower value. But wait a second. Why doesn't it affect this one? And this one either. So, and this would be the. I'm a bit lost right now into how to reason why this affects which ones this affects. That bottom wire. But if we're having the swaps, this is affecting the TAM representation. Is it? But it shouldn't really. That control T. Oh well, it's a control T, which is so it affects only. It only applies when that wire is 1. So that wire is 1. So it applies always. Yeah. When that wire is 1. Which is, of course, 1 everywhere. So this control T should be applied for the last oh, it applies where the last qubit the one from the right is a 1, of course. And the same here. Oh, yeah, because at the end of the day, it's a... Oh yeah, because that's the definition of a control set, right? Ah, the control set only works when both qubits are 1. So it only works for the one component because it's a relative phase shift. Ah, basics. Basics, but that's why it only affects those. So, but it's quite impressive that this is really creating the actual final effect you want, right? Um, because it's leaving those unchanged. Pretty neat. Pretty neat. Um, there's something feels off actually. Something kind of doesn't feel right. I mean, eventually, that's the idea. Is eventually, because you're doing a superposition, there's always going to be some term that you're rotating because there's always going to be some term in each of them that is a 1. Of course, with the exception of the first box, which is like all zeros, and that obviously doesn't rotate at all as it shouldn't. So, like it shouldn't, like it's supposed to behave. So that's good. So that's fine. Now we're adding a Hadamard in here. And so what this does is it basically widens our superposition. But because this wire is a 1, that's the interesting thing. So so it's basically, what it's doing is it's literally mirroring what we had. So this is what we had, and it's literally mirrored, right? So this is what you kind of see here, but the existing phases are all mirrored. That's an interesting effect. How to think in terms of, because intuitively in the beginning kind of makes sense, but when you dig into this, it's actually hard to reason about. It's a bit, it feels there's something kind of hidden in there. I don't know, it just doesn't feel right. Okay, but you see the role of those Hadamard gates is to kind of, create the different, like, bring you to a full superposition. It's just that while you're doing that, you're rotating the things accordingly. And so the next step, which I can also break down into into different rotations, just so we get the full picture of it. So what has happened in here? There were nothing really. Oh yeah, of course nothing happens because that qubit here is 0, so none of this is really activated, so nothing happens. I'm gonna skip all that. Gonna jump to the last Hadamard, which basically takes the whole thing and copy pastes it. So so it takes this whole thing here, right? And it's just copy pasted in here, because at the end of the day, at the end of the day, you already have half of the wave, or so half of the encoder wave. So you just want to copy paste that. So that last Hadamard is always gonna copy paste that, unless I'd say unless that last qubit is, whoa, oh crap, oh, okay, but I lost my annotations. Anyway, unless that last qubit, or in this case this one is set to 1, in which case if I do that, so what's going on now? Now it is set to 1, so this is the same. So here we got the same pattern. So those two get like up, then those two get affected, and then you've got a Hadamard gate on a qubit that is a 1, right? Because it's coming from here, and so that has the copy paste plus mirror effect, copy paste plus negation. But that's really also, you know, what I was. It's interesting because that's how Xanadu defines the Fourier transform gate. Is like position equals minus momentum, I think, and momentum equals position. Because it's a minus, right? Like the mirroring, it's really a minus here. So you're basically telling. So this is kind of mirrored in here, and then copy, like, I mean, it doesn't matter how you put it, right? But you can think of it in different ways. It's like copy pasted here, and then there's like a mirror effect. But now probably should take a look, because now this one is a 1, this wire. So we should probably take a look at what's happening here in between. If we do these, so now what we have got is that for the elements that have a 1, which are only these ones in here, we're applying another S rotation. Another S rotation. So S. So we are basically rotating by 90 degrees each of them. So that's minus 45 degrees. It was minus 135. Yeah. Then when you got a T. So what this is doing, my God, it's rotating, or this is a 1, so it's rotating only these 4, right? Yeah. These 4. And then you got like a rotation of 1/8 of the last qubit of this one here. So it's 1 every 2, right? And then the final Hadamard here, it basically does the same copy and mirror. So it copies it here, and then it mirrors it here, and voila, you got what you wanted. So we should have we should see here 3 full turns, 3 kind of. So you start here, then you're rotating counterclockwise here you've already passed the half iteration. It's like half circle. You keep rotating, so roughly here is where you where you already kind of go through the second loop. So rotate, 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 rotate. Around here is when you go then you go over from the second to the third loop, and then you go all the way here, and then yeah, obviously that's not, it's, you know, you can't capture the full 3 circles, but that's all you can do with the resolution you have. That's kind of, that would be the resolution. It's what's defined by the amount of qubits you're using. So 3 full circle cycles. This is one, this is the other, and this is the other. But it's much more complicated to look at it step by step, um, because basically there's a lot of bits and pieces going on. But the Hadamarts basically take care of what do they take care of? The Hadamarts take care of the fact that that one, you finally get a superposition, and two, they correct also, by definition they also correct the like the phase by 180 degrees, because the ones, definitely when you've got a 1 in here, right, that makes you that makes the leftmost qubit switch to 1, because that's, you know, that's what you want. You want to control those rotations. You want to control rotations for all the below qubits, or above in this case, but like the ones that are like following this qubit. But at the same time, when you do that, then you know that your superposition is going to start up here, like down here. And so you want to correct at the end. What you want to do is, you know, that's, you want to locate that into the beginning of a superposition, and then basically flip that, right? And so intuitively, this is a superposition that was basically initially seeded by a 1. Not seeded by a 0. And so, but here we've got a 1, so the last Hadamard takes care of that correction. Yeah, but I have the feeling that I'm kind of just accepting some things, and I really don't want to do that. So I'm not extremely happy. Not extremely happy. But it's, I mean, it's what it's doing, right? So each of those qubits, they have an importance within the number, like they have like an actual weight, like in the sense that, you know, if with 4 qubits you can with 4 beats you can represent 16 numbers. So each beat kind of has a weight into how much of this number this represents, right? Like this has this beat in this case has the highest weight, because if you switch it to 1, you basically go from 0 to, like, you know, 8, right? And so but then in turn the 8 should have if you've got an 8 in here, you want basically that that all the that all the previous elements in this that all the other qubits in that rotate as well, because you need a more granular rotation, right? No, you need a Roth. Oh, how to reason about this in a way that it's not confusing? Because intuitively I feel comfortable with it, but I still feel I'm accepting some facts that I'm not like fully aware of. Um, so the one, oh yeah, so the one here is the one. Okay, so let me put it exactly. So if you the eight, the 8 in here, I was saying this in the wrong way. So the 8 in here has a big weight, has the highest weight in the whole, like, from all the qubits, because if you switch it to 1, it represents an 8, which is half of your 16. But in the terms of the QFT, it should have the smallest impact on rotations, because basically if you just got an 8, it means you want to have 8 turns within your 16 boxes, which means it's a really rough, like it's a really aggressive kind of turning. It's not really granular, so you just have like um, you have kind of your if you're rotating the qubit that's here on the top, it's the qubit on the rightmost, so this means that the rotation there will directly um, affect mm, what does it mean actually if you've got like a if you've got 8, yeah, yeah, basically that's what you have, of course. So you have an 8, so uh, the one goes here, right? And so you've got like you've got a Hadamard that does this for you. Then you just got a bunch of Hadamards that then when they are enabled, they just copy the whole thing. They keep copying, right? Nothing else is activated, and then only this one is activated. Sorry, these three. Uh, but why don't they have any impact? Oh, what am I saying? I'm so stupid. I'm just dyslexic or something. I don't know. So, oh my god, the one goes here, obviously, up here. So this nothing is just, the Hadamard. It's all that happens. Just the Hadamards are. Then the QFT is just Hadamards in this case, because yeah, because basically if you want to have 8 turns within 6 boxes, be, then the difference between each box should be already like an 180 degrees rotation, which is already what you get with a traditional Hadamard. That is seated by a 1, of course. That is 8. So if you go this way, then it's a different story, because uh, then you got like really Roth rotations, because you got 16 of them, 15 of them, sorry. So you got the weird effect that it looks like it's running clockwise when it should be kind of counterclockwise, and it is, because it between this and that it almost does a full turn. So, but in that particular case, it's almost like, imagine. Mm, So it's almost like, okay, so it's 111. So basically, what's going on here is like, doesn't matter. Here in this case, the swap gates don't make any difference, and so and everything is activated. So the controlled S makes this pattern, then well, makes this pattern. Then the Hadamard basically, the Hadamards are kind of copying that, all that. Then basically control S in here. So you're, for every new Hadamard you're adding, you gotta correct the rotation. You gotta correct the rotation because because you're adding more more possibilities into your mixture. But then the upper you move, or in terms of here, the more you move to the left, the more granular those rotations must be, because how to reason that? So let's try to think about it in terms of 2 qubits. So we've got this, we've got these, and these as 4 possibilities. So mm, mm, uh, basically what's the reason why you should use an S and a T is because so you're basically moving from 2 states to 4, right? So when you move from 2 states to 4, you need to make that rotation more granular because you want to have the same effect. So what you want to have, right, exactly. So what you want to have is, so you want to have, this is what you represent with, this is the information you represent with these two possible amplitudes. So with these 2 possible boxes. Something's not right. Doesn't match what I wanted to say. You want it to be more granular. So when you're doing a Hadamard, in this case it's all ones, the more ones we have, the I don't know how to reason about it. Okay. Oh man, it just feels so stupid. Like it just feels so simple that I can't understand why I'm not able to figure this out. Or it's not. It's that I'm not able to explain that in a way that it makes sense, even to myself. This Hadamark just copies that, but flips the sign, so you gotta correct that. By applying a Control S and a Control T. And the control S you apply to here, here and here, here and here, here and here, and the control T is applied here and here. Oh yeah, of course. Uh, and that's why because the effect of those gates is where the number one is, and because of this is like a base 2 system, right, like binary. So that's why like the influence, the influence here would be on these two boxes, but then this one is gonna, sorry, I'm running out of colors. This one is gonna influence this one and this one. So what you wanna, so uh, that's why you're rotating like a power, like you're rotating a power of two less, so to say. So you're creating this effect of, in between these and these, you should have sort of what's in between, right? And you do that by rotating less, but how much less is indicated by how much influence that that beat has in the overall beat string. Yeah, I think we're gonna have to stick with that. That makes sense to me. Um, as I said, it's kind of unfolding. I just wanted to make sure that I'm not like, you know, as I said, I have still the weird feeling that I'm assuming. I have the weird feeling that I'm basically taking something for granted, and I don't want to do that. So I don't know. Maybe it'll become obvious. Maybe it'll become more obvious when I take a look at the inverse of that. So at the QFT. Um, but I think that's clear enough. So the hotmarts have that role of copy pasting, so creating your superposition step by step. But at the same time, they also kind of flip if needed. If the actual qubit has a 1, they also add phase in that they basically flip the entire part, like they copy and then they kind of flip the phases on the other side. um, and then the control rotations have that function of, when this is when this is 1, right, when this is 1, this is gonna affect, is gonna generate, gonna trigger a chain of rotations for all the other qubits up here, and at the same time it's gonna trigger a the Hadamard seeded by a 1, which is basically gonna have a copy plus negate effect. Um, so those are the two components that are the most important here at play. Yeah, and then at the end you get what you want to get, which is that beautiful thing here. Cool. I feel quite comfortable with it. I have that weird feeling that I'm saying, but maybe that'll become more obvious if I take a look at the other one. Perfect.